In Chapter 16, Section 6, we're going to look at parametric surfaces. So if we look at the first problem, it says identify the surface with the given vector equation. So basically a main giveaway is if there's not sines or cosines, you're not going to have these curved surfaces. So without sines and cosines, you're not going to have the circular cylinders, or hyperbolic paraboloids, or elliptical cylinders, or circular paraboloids. And I should say, I have to be a little careful there. Sines and cosines, or something squared. So having things squared can provide you with circles, right? So if you have u squared plus v squared, that's probably a circle. So these are all just linear terms in I, j, and k with v's and u's, so they're lines. So in 3 dimensions, that's going to be a plane. So pretty simple for the first one. For the second one, this time we will get a hyperbolic paraboloid. So we're going to have s and t. So in the x and y coordinates, this is linear. But then in the z coordinate, you've got a parabola, and the way these are going to connect is from these linear terms to this parabolic term. Those are going to be hyperbolic connections. So you're going to get a hyperbolic paraboloid. And the e-text kind of outlines different forms of these parametric equations and what the actual thing will be. So I'm not going to really go over each one because you can kind of look it up in the e-text. So for example, if you look up in the e-text something that has the form of a sine and a cosine in one of the two terms, and then another variable, say squared, then that's going to be a circular paraboloid. So if we square these two terms, so if we square, this would be s squared sine squared of 4t plus s squared cosine squared of 4t. Well, this equals s squared times sine squared of 4t plus cosine squared of 4t, which is 1. So this whole thing is s squared. And so in one of these planes, let's see here, so that's x and z. So if we have x, y, and z, in the xz plane, it's going to be hard to draw. Let me actually extend this. So in this xz plane, it is a circle of radius s. But then in the y, it's s squared, so this thing is going to grow according to a parabola. So in the y direction, this thing is growing like s squared. And so this circle is basically going to grow as this goes out like that. So it's going to be a circular paraboloid. Okay, so that's one example of how you would handle that. Okay, now for 4, we have a vector r that's a parametric vector in terms of u and v, and we have sine v in the x direction, cosine u sine 2v in the y direction, and sine u sine 2v in the k direction. And again, I would kind of refer us to the book and look up what happens when my x term is sine v, what happens when my y term is cosine u sine 2v, or sine av, just some constant, and when is z sine u sine 2v. And it will have a picture that looks like this one right here. So it will show you this picture, and so you can grab that, and now we just have to interpret this picture. So it's going to say, what happens if we make u constant? So if u is a constant up here, not a variable, then we're going to get grid curves that lie in a plane z equals ky that includes the x-axis. So we're basically going to get this cosine is a constant, and this sine u is a constant. And so in the x and z directions, we basically have two constants times the exact same thing, sine of 2v and sine of 2v. So we're going to have these grid curves. Okay, so let me try to draw this. This might be kind of tricky. So we have the grid curves are lying in the plane z equals ky. That includes the x-axis. So we're going to have x, z, z, y. And if we were to look at this, with u being a constant now, it's going to look like if z is equal to ky, then when y is 0, z is 0. And when y is 1, z is k. And when y is 2, z is 2k, according to this. And we're going to get kind of a plane that's going to go through the x-axis but go up like this. So we're going to have something that's going to go up. Boy, this is hard to draw. Like that. And it's also going to go down through this part too. So, and with this double curve here, these things are going to look like, these grid curves are going to look like kind of like these hourglass shapes. Okay, so it's like slicing through this thing, and we can see how it's got this hourglass shape to it. Okay, so that would be if we made u a constant. I think it's actually easier to see the next one. So if we make v a constant, what we get is the plane x equals sine v parallel to the yz plane. So we get, these should be circles. So it's like x, y, z, and now we are taking v to be a constant, so we're slicing into this shape over here. Color did I use? Blue. At any point, let's say I do it right here, and create a plane here, a slice through this thing, like that. Well, if I were to look down that x-axis, I didn't draw this very well. If I were to look down that x-axis, I'm going to see a circle. So any cut in here that we take, so I take a cut closer to the YZ plane, it's going to be a smaller circle. And their circles are going to shrink until you get to the origin. Okay, so that would be what we get for the grid lines if u is a constant. Excuse me, if v is a constant. Okay, and that is problem 4. Okay, problem 5 is very similar. we have, again, we have these three equations, and we look these up in the textbook, and they say, oh, these will look like that. So we can pick the shape based on those three parametric equations. And if u is a constant now, we're going to get a circle of radius 1 minus u in the horizontal plane z equal u. So this one's pretty simple to see. So we have x, y. We're looking straight down the z-axis, so it's coming up at us. Looks like the tip of an arrow when you draw it like this. And if we're looking down at this thing, and I take a slice anywhere, we're going to have circles. So imagine just looking straight down this thing, and we're going to get these different grid line circles. Okay, so that would be the first one. And then the second one, if v is constant, we get, okay, so if we draw this one, and now v is a constant, we're going to have, these grid lines are going to run along the planes y equals kx. So we're going to have y is 0 when x is 0. When x is 1, we get y is k. When x is 2, we get y is 2k. And these things should connect. So we're going to have and z is free to do whatever, because u, so if we look back, we can't see it now, let's look back. Z is u, and that's not a constant in this one. So it's going to vary. Otherwise, these are going to be planes that go like this. So we have these planes, and if we can imagine cutting this thing at these various points, the resulting curve is going to be straight lines. So we're going to get curves that look like this. Okay, so that would be problem 5. Okay, so problem 6, we're going to have a little more arithmetic to do. So we have the parametric representation of the surface. We have the part of the sphere, x squared plus y squared plus z squared equals 64. Above the cone, z equal to square root of x squared plus y squared. Okay, well, the first thing we're going to do is we're going to say, substitute this in for z. So we're going to get x squared plus y squared plus square root of x squared plus y squared squared equals 64. When we square that square root, it's just going to be x squared plus y squared. And in essence, we can factor out x squared plus y squared, and we get 1 plus 1, or 2 x squared plus y squared equals 64. Therefore, x squared plus y squared equals 32 when we divide both sides by 2. Okay, now we're going to say, well, that is the same as z squared. So z squared has to equal 32, therefore z is equal to the square root of 32. And now we're going to say, we're going to let, this is where the parametric aspect comes in, we're going to let x equal u, y equal v, and if we do that, then z, which we solve for right here, is going to be, actually, how do I want to write this? We would say, from this equation, z squared is 64 minus x squared minus y squared. And then to get z, we're going to take a square root of that. So it's going to be square root 64 minus x squared minus y squared, but we just changed x and y to u and v respectively. So we're just going to write with commas in between them, x equals u, y equals v, and z equals the square root of 64 minus u squared minus v squared. Okay, so that would be the parametric representation of this sphere that lies above some cone. For problem 7, it's very similar. We have x squared plus y squared plus z squared equals 4. And that is going to lie above, between the planes, z equal minus 1 and z equal positive 1. Okay, what else am I missing? I think that's it. So we are going to put this in spherical coordinates. So in spherical coordinates, because we're dealing with a sphere here, so this is a sphere. Now the last one was a sphere also, but we were dealing with a cone and not between two planes. So we could, and we could have written the last one in spherical coordinates, but it actually said write it in terms of u and v. This one says write it in terms of theta and phi, which are the angles we use for spherical. So in spherical coordinates, we're going to let x equal to the radius of the sphere, which is going to be 4 squared. So this is equal to rho squared, the radius of the sphere, so rho equals 2. So normally x would equal rho, and then it would be sine phi, cosine theta. Y would be rho sine phi sine theta. Make sure I got this right. Yep. And z would equal rho cosine phi. Well, we know all these things. X is going to be 2 sine phi cosine theta. Y is going to be 2 for rho sine phi sine theta. And z is going to equal 2 cosine phi. Okay, and I guess that's it. But I want to show you a little more than just that. That's all you need for the answer, is to write those out. So you just need the radius of the sphere and then to put them into these forms. But if we wanted to solve this, which we will look at, kind of we'll do some areas of these things, calculate these values. So let's look at in between the plane z equals minus 1 and z equal 1. So we can plug these into, in this one, into the z formula. And by doing that, we can see how phi is going to vary. So we can say when z is minus 1, that equals 2 cosine phi, which means minus 1/2 equals cosine phi. And therefore, if you look on unit circle, when does cosine equal minus 1/2? Well, that occurs at 2 pi over 3. So phi equals 2 pi over 3. Then we can say when z is 1, we'll get 2 cosine phi, which means 1/2 equals cosine phi. And again, on unit circle, look up when does cosine equal 1/2. That happens at pi over 3. So we're going to have, for our limits of integration, theta varies from 0 to 2 pi, so that one's going to go all the way around 360, but phi is going to vary from pi over 3 to 2 pi over 3. And again, so that will help us set up the limits of integration and actually be able to find these areas, or volumes. Okay, and that's problem 6. Oh, problem 7, excuse me. So problem 8 says find the area of the plane, 5x. So we want to calculate area of a surface, and that's going to equal the double integral of the square root of 1 plus, in 3 dimensions, we're going to have dz dx squared. It's actually, well, it's 2 dimensions really, because we're going to solve for z, dz dy squared dA. So this is the formula we're going to use. And so we just need to solve for z. So our equation is 5x plus 2y plus z equals 10. And we will subtract everything from the left side. So we'll get z is 10 minus 5x minus 2y. And just from that, we can find dz dx is -5. dz dy would be -2. So partial derivative with respect to these letters, everything goes away except for the -5 and the -2 for x and y respectively. And we'll plug that into this formula. So we're going to get the area of the surface is going to be this double integral across region D, square root of 1 plus dz dx is -5 squared from the formula, plus dz dy is -2 squared from the formula, dA. And this is going to be, I'm going to pull it out of the integral in fact, 25 plus 4 plus 1 is root 30 times the double integral of this differential area. And we can find that area. So it lies in the first octant. I think I am going to do this one with the double integral. So we imagine that z is 0. So we're looking at the xy plane. So we have z is 0. So we're looking at xy. The z would come out of the page at us, but it's 0, so we're right on this bottom plane. And we're going to imagine that, so we're doing this equation, but z is 0. If z is 0, when x is 0, our y value has to be 5 for this to equal 10. So when x is 0, our y value has to equal 5. And when y is 0, our x value has to equal 2 to equal 10. So when y is 0, x is 2. And there's basically a line in between them. Okay, and so we're looking at this region here. This is D. And in that, we have x varies from 0 to 2. And y varies from, this one's a little trickier, y goes from 0 to this line right here. Well, this line is y is equal to 5 minus 5/2 x. And you can get that just by using these 2 points, 2, 0, 2 in the x, 0 in the y, and 0 in the x, 5 in the y. So use those 2 points to get the slope, and then you can use point slope form to get this equation. So we're going to go from 0 to 5 minus 5 halves x, and then our order of integration would be dy dx. This will equal root 30, 0 to 2, of just y from 0 to 5 minus 5 halves x dx, which is going to give us root 30, 0 to 2 of 5 minus 5 halves x dx. Okay, and then the antiderivative of this would be root 30 times 5x minus 5 halves x squared over 2 from 0 to 2. This would be square root of 30 times 5 times 2 minus, this is going to be 5/4 times 2 squared minus 0 minus 0. This is basically 10 minus 5, so we get root 30 of 10 minus, this is 5 times 4 divided by 4, so the 4's cancel, so it's 10 minus 5, which results in 5 root 30. So that would be the area of the part of the plane that lies in the first octant in 3 dimensions for problem 8. Okay, problem 9 is really pretty similar to this. We have the part of the plane x plus 2y plus 3z equal 1 that lies inside the cylinder x squared plus y squared equals 8. Okay, and so again, we are going to solve for z. So we're going to say z is equal to, so I'm going to do a couple steps in one here. We've got to subtract everything and divide by 3 because there's a 3 in front of z. So it's going to be 1 over 3 minus 2x, but it's going to be 1/3 x. Because we're dividing everything by 3, and it's going to be minus 2/3 y. And therefore, partial z partial x will be minus 1/3. Partial z partial y is minus 2/3. And the area of this surface should be this differential area times the square root 1 plus dz dx squared plus dz dy squared dA. Okay, so we're going to get the area of the surface is the double integral in region D, square root 1 plus minus 1/3 squared plus minus 2/3 squared dA. And this is going to be square root of 1 plus 1/9 plus 4/9 dA. The area of this is going to be, this is just going to be the square root of 5/9 plus 9/9, which would be 14/9, and that can be outside of the integral now, of d dA. But this region is the area of the circle. So it's this is a circle of radius r when z is 0. Circle of r equals square root of 8. So this is the area of that circle. So it's going to be pi times radius square root of 8 squared with this square root of 14 over 3 in front of it. How do I get 14 over 3? So you can take square root of 9 and make it 3, and take square root of 14, leave it on top. This square root of 8 squared will become 8, so we cram this all together. It would be 8 pi square root of 14 all over 3. And that would be the area of this particular surface for problem 9. Okay, last problem in this set, we have find the area of the surface, and we're given parametric equations. So it says x is u squared, y is uv, z is 1/2 v squared, and then it says u is sandwiched between 0 and 5, and v is sandwiched between 0 and 3. And for this one, we're going to use a slightly different equation. It's going to be the area of a parametric surface is going to be the double integral across region D of the magnitude of the partial derivative of vector r with respect to u cross product with the partial derivative of vector r with respect to v dA. Now I just said a mouthful, so let me show you what all this means. Let's break this down. So RU, how do we want to write this? So RU is going to equal the partial derivative of x with respect to u, which is 2u, the partial derivative of this y term with respect to u, which would just be v, and the partial derivative of z with respect to u would be 0. Then we have RV would be partials of those same three equations, but with respect to v now. Partial derivative of x with respect to v, there are no v's, so that's 0. Partial derivative of y with respect to v would be u. So v is a variable, u is a constant, the v goes away. Partial derivative of z with respect to v, the 2 would come down, cancel with the 1/2, subtract 1 from the 2, it's just v. But now we have to cross product these. This is a good cross product review. It's going to be I, j, k. First the RU vector, 2u, v, 0. Then the RV vector, 0, u, v. This is going to equal, you cover up the I row column and the I row, and you're left with a 2 by 2 determinant of the bottom right four things. So you take v times v, v squared, minus 0 times u, which is 0, and that's in front of I. Then cross product says minus, so it's plus, minus, plus. And for the j term, you cover up the j column, and you're left with 2u top left, 0 bottom left, 0 upper right, and v bottom right. So you're going to take 2u times v, 2uv, minus 0 times 0, which is 0, in front of the j term, and then it's plus, cover up the k column, and you get a 2 by 2 determinant. 2u times u is 2u squared, minus v times 0, which is 0, in front of the k term. So this cross product is the vector v squared, comma, minus 2uv, comma, 2u squared. Okay, now the magnitude of that equals the square root of the sum of these things squared. So it's v squared squared, which is v4, plus minus 2 squared, which is 4, u squared, which is u squared, and v squared, which is v squared. Then it's plus 2u squared squared, so it's 4u to the 4th. But this can be written, if you look very carefully, as v squared plus 2u squared squared. So it just so happens that this thing can be factored into a perfect square, v squared plus 2u squared. If you were to FOIL that out, you would get back to these three terms. And this square and this square root will cancel, and you're left with v squared plus 2u squared. Okay, that is going to replace this right here. Not the dA part though. Just the magnitude of the cross product. So we get a double integral, and let me make sure I do the order the same way I did my notes so I don't have to think too much on the fly. We're going to have 0.503 of v squared plus 2u squared, and I believe I'm doing dv du. So we're going to get, this is 0 to 5 of v cubed over 3 plus 2u squared v from 0 to 3 du. So that's going to give us 0 to 5 of 3 cubed over 3 plus 2u squared times 3, and then minus 0. The 0 bottom limit will just drop everything away. So this is 27 over 3, which is just 9. So this is the antiderivative from 0 to 5 of 9 plus 6u squared du, which equals 9u plus 6u3 over 3 from 0 to 5. So it's 9 times 5 plus 2 times 5 cubed minus 0 plus 0. So we get 45 plus 2 times 125, which is 250, plus 45, 295. So that would be the area of that particular surface of parametric equations. Okay, that will conclude Chapter 16, Section 6.